covalently bonded atoms. That is the atomic nucleus. Or you can simply say the atomic radius or size is the distance from the nucleus of an atom to the outermost electron. Whichever way you say is correct. Then the atomic size, we have to know the trend of all the properties we are discussing now. The trend is either across the period or down the group. As a thumb rule, whatever property that increases across the period will decrease down the group. And whatever property that decreases across period will increase down the group. For the atomic size, across the period, it decreases. Down group, it increases. So, how do I got to conclude these two? It's based on three principles. So, factors determining atomic size or radius. The first of them being the nuclear charge of attraction. Nuclear charge of attraction. The second being the screening or the shielding effects. Okay? Then the third being the distance of the outermost electron. Distance of outermost electron from the nucleus. Let's briefly bisect these three determinants now. For the nuclear charge, let's see the nuclear charge across the period. Now, if we take any particular period, you will observe that this is how it occurs. In the period, all the elements in the period, they have the same number of shells. So there is no increase in shell. The only thing now, of course, is that there is progressive increase in number of electrons by 1. So if this is the first one we come across, this is 1 electron, 2 electron, 3 electron, as we go from left to right across the period. And of course, there's a law that says like charges repel and unlike charges attract. Positive will attract negative, while negative will repel negative. So, electrons are negative, of course, we know that, okay? While the nucleus is positive because it contains the proton, which is positively charged. So, because the electrons are negative, they tend to be pulled towards the nucleus. And as we go from left to right, more electrons are being added, hence there will be more pull. If there's more pull, the atom is going to shrink, going to get decreasing in size across the period. So as I said, across the period, the atomic size decreases. Now that pull I just mentioned is due to the nuclear charge. That nuclear charge is what exists between the negative and the positive. So there's a charge difference. So the charge now will be pulling them together. This is one. Then the screening effects. This one comes into play when we are discussing down the group. So let's see down the group. Now, of course, down a particular group, there is, for across a period, there is a progressive increase by 1 electron. But down a group, there is a progressive increase by 1 shell. So if this is down the group, the first one has 1 shell, second one we have 2, third we have 3. So this one we have 2 electrons. This one we have 1 there and 8 here. Okay. This one we have 2 here, 8 here, and 1 here. It will be very easy for this electron to be put to the nucleus here, but it will not be that easy. I think I should make my diagrams bigger so that you can see it well. So what I'm saying for the screening effects, this is the nucleus positive, and this is an electron. Then when you go down a bit, this is another nucleus positive. The first electron with 8, the first shell rather, with 8 electrons. The second shell with, let's say, 1 electron. Then when you go down again, that particular group, you have the nucleus with the first electron, the first shell having 8 electrons, second shell having 8 electrons also, the third one having 1 electron. Now let's see carefully. If this is a fire source, and somebody is standing here, somebody is also standing here, you will agree with me that this fire will hit this person A more than person B. Why? Proximity. Before it gets to person B, person A is kind of shielding person B from this adverse heat. That one is what is going to be happening here. So in the case of the screening effect, the atoms that are closer, the electrons that are closer to the nucleus are going to shield away those electrons that are farther away from the nucleus. That is the screening effect. Because that screening effect, the nuclear attractive force is not really that predominant or effective in pulling them together. So as more and more shells are being added progressively down again, there will be an increase in the atomic size as we have just depicted on the board. Okay. Now, there's something of note. When elements, let's say this is an element, this is the K, this is the L. If an element leaves the K shell, an electron leaves the K shell to the L shell, it is said to be excited. But if it goes the reverse from the L to the K shell, it is said to have returned to its ground state. Ground states. While if it goes from low to high, it is said to be in the excited state. Why are they in excited state? They are in excited state when they gain energy, and they return to the ground state when they lost that energy. So let's look at the families of elements. The first one, okay, we've discussed the families of elements already. So the next thing we want to look at is there was one important property of the transition metals I failed to mention, and that is they are employed as industrial catalysts. Please forgive me for not breaking from time. Industrial catalyst. A catalyst is any substance that makes a reaction to occur that alters the rate, either increases it or decreases the speed of the reaction. So, by that, we have what is called the Haber process. Haber process. The Haber process is a process industrially used to produce ammonia gas from hydrogen gas plus nitrogen gas. So we now have ammonia gas. Ammonia is a gas, okay? Nitrogen is 1, hydrogen is 3. So hydrogen is 3. So hydrogen is now 6. So we have the ratio of 3 to 1, ratio 2. Then we have the contact process. The contact process is a process where SO2, that is sulfur 4 oxide, plus oxygen gas gives us SO3, sulfur 5 oxide. Okay? S is 1, oxygen is 4, oxygen is 6, oxygen is 6, so it's balanced. The next one is number 3, is what is called the hydrogenation of alkanes to alkenes. Sorry, it's supposed to be of alkenes to alkanes. While fourthly is the hardening of oil to form fat called margarine. Alright. Then the fifth is in the decomposition of peroxide to give us water and then the oxygen. These are other examples are where we see transition metals employed as catalysts. So in the Haber process, we use finely divided iron as the catalyst. And in the Haber process, the ratio of nitrogen to hydrogen is 1 to 3, or hydrogen to nitrogen is 3 to 1. In the contact of the Haber process, in the contact process, sulfur 5 oxide is produced from oxygen and the sulfur 4 oxide using vanadium 5 oxide, V2O5. Vanadium 5 oxide. In the hydrogenation of alkanes, it is an important reaction that the of the alkenes that they undergo. And in this reaction, the alkenes will now attain a saturated state of the alkanes, because alkanes are saturated at the carbon, while the alkenes are unsaturated. So what is employed here is nickel, divided nickel granules. Same thing for the hardening of oil. So hardening of oil and the hydrogenation of alkenes to alkanes employ the service of nickel, while the decomposition of hydrogen peroxide to give us water and molecular oxygen employ the service of manganese 4 oxide. Manganese 4 oxide. We now get water and then oxygen. Oxygen is 3, okay? It's just to balance the equation. Oxygen is 2 here. So if I should have 2, it therefore becomes balanced. So this is the summary of the periodic table. We have seen the history, the blocks, SPPF, group 1, group 1 to 8, the periods. We've also seen the configuration, transition metals, and the periodicity. Okay. Now, back to the periodicity again. So the periodicity, I mentioned at 1 atomic size, where I said it decreases across period and increases down the group. So in exam, if I bring 2 elements like lithium and potassium and ask which one has a higher atomic size, of course you know that going down the group, atomic size is increasing. So potassium will have a higher atomic size than lithium. Okay. Then, having said that, we now look at ionic size. We are to look at ionic size. Ionic size. Ionic size. Ionic size of, let's say this is O2 minus and this is oxygen. This is the ionic form of oxygen and this is the neutral form. The ionic form of non-metals have greater ionic, the ionic form of non-metals have greater ionic size than their corresponding neutral atoms. That is for non-metals. So it therefore means that Cl minus is greater in ionic size than chlorine as a neutral atom. The reverse is obtainable for the metallic element. The ionic size of metals like magnesium 2+ is lesser than its corresponding neutral magnesium atom. Same thing for aluminium 3+ is lesser than normal magnesium. So that is for the ionic size. Then there's something else called isoelectronic species. Isoelectronic species. Isoelectronic species. When we talk about isoelectronic species, iso means the same. So it therefore means that these are species which have the same electron configuration. Invariably, we are saying that these are species whose number of electrons are equal. Remember that the identification of every element is the atomic number. No two elements have the same atomic number, but it is possible for 2 or even 3 elements to have the same electron number, and that is the phenomenon of what? Isoelectronic species. So let's take a talk into those elements that have this phenomenon. We have oxygen. The neutral form of oxygen is 2,6. But when oxygen gains an electron, it forms oxygen ion. So this becomes 2-. Because it has gained electron, it's no longer 2,6, but instead it's now 2,8. That is one. Then fluorine. In the normal state, fluorine is just 2,7. And it requires 1 electron to make this to be in the octet state. So if it gains that 1 electron, it becomes 2,8. And non-metals, when they get electron, they become negative. If it is 1 electron they gain, -1. Why is here 2-? Because it was 2 oxygen gained. Then we have neon. Neon in its ordinary state, of course, neon is a stable electron element, is 2,8. We have sodium. Sodium is 2,8,1. But when sodium loses an electron, it becomes 2,8. Another example again is magnesium. Magnesium is 2,8,2, that is 12. Lose 2 electrons, it becomes 2+. Aluminium is 2,8,3. Lose 3 electrons, becomes aluminium plus, 3+. So all these examples are referred to as isoelectronic species. So in the exam, if you are given, you may not be given all these examples. You might be asked what is common between O2-, neon, and magnesium 2+. They are just what? Isoelectronic pairs or groups. Alright. Another example of isoelectronic pair, this is example 1, is found in chloride ion. Chlorine is 2,8,7, that is 17, and it can be stable by gaining 1 to become 18, that is 2,8,8. After chlorine, then we have argon, which is 2,8,8, already stable. Then we have potassium, which is 2,8,8,1. Loses an electron, becomes potassium ion. And then we have calcium, the last on the list, which is 2,8,8,2. Loses 2, becomes 2+. So chloride ion, argon, potassium, and calcium ions are another example of isoelectronic species. One thing you must remember from isoelectronic species is that their ionic size is inversely related to their atomic number. What do I mean? Those that have higher atomic sizes, we have a lower ionic, those that have higher atomic numbers, we have a lower ionic size. For example, in this example 2 I left here, calcium is 40, atomic number 40, atomic number, is 20, here is 19, here is 18, here is 17. So if you are asked an exam to arrange, or they arrange for you and they ask you which is correct. So what you do is that from this we can, if I want to arrange them in increasing order now, so that means starting on the list, that means the one that has the lowest ionic size, I will now go to calcium because I said that the one that has the higher atomic number should have the lowest ionic size. So it becomes calcium less than calcium ion, less than potassium ion, less than argon, and less than chloride ion. So this is how we do it. This brings us to the end of periodic table. Alright? So do not forget I said metals are strong reducing agents and non-metals are strong oxidizing agents. Till we meet again, I remain favored and stay tuned. If you like the video, click, comment, like my videos, share it, and stay tuned for more interesting videos on how to make you the best student in your school. I remain favored.